would like to thank the organizer, Christophe Pouet and Philippe, for this very nice meeting. It's a great pleasure to be here, especially to talk about classification of sparse high-dimensional vectors, because this work was done with Inster 2 or 3 years ago, so the paper is almost ready, but we have to submit it. So it's a emotion to be here. So as you all know, classification is a fashion word. We have also sparse and high dimensional. So we put all this together. This work, in fact, is an extension of a work we did with Sasha Tsibakov and Yuri Ingster about the classification of sparse high dimensional vectors, but there is a small difference in the number of classes we consider. So the outline of the talk will be the following. I will present the classification problem. Then we will write 2 cases. There will be one moderately sparse case and one highly sparse case. And I will talk about some extension, in fact some results we have, but I will not present here. So about classification here, we will assume that there are in fact MID samples with M greater than 1. And these samples come from M different populations. So we will have our observation. In each population we will have a sample of size Nj, and each observation is a d-dimensional vectors with some random probability measure Pj. And then we observe, as usual, a random vector Z of dimension D, and we would like to classify this vector. That is to say, to tell which class belongs Z. So we have 2 goals: find a good classifier, but as you will see, I'm not really interested in computationally tractable classifier, in fact. But our main goal is, in fact, to find conditions to discriminate between good and bad classification problems. And this is our main aim, in fact. That is to say, to have a kind of optimal phase, position phase plan. So what we will assume? We will assume that our vectors coming from the different population are just a shift of a Gaussian vector. That is to say, we'll have UKIJ. So there is a lot of indices, as you can see. And then we add some random errors. And then our vector Z will be of the following form. Zk will be UK plus some error also. So as I said, our errors are IIT random variables, centered, Gaussian, and with sigma squared variance. But as you will see later, I will assume that sigma squared is equal to 1 in order to have a much more simpler result. And as I said in the title, we will assume some kind of sparsity. So we have a set of sparse vectors in Rd, which is UD beta A. It means that we have some signals on some coordinates, and the number of coordinates which are the signal is between d power 1 minus beta and d power 1 minus beta with some constant. And in fact, we will let the constant go to 1, but it's not a problem.
Wait, epsilon t takes value 0, 1?
Sorry?
Epsilon t takes value 0, 1?
Yes.
Okay.
Okay. One short comment that we will assume that there is always a class with no signal. So we can do without it, but it's much more convenient to have this kind of class in order to always classify a signal. So as we have, in fact, M population, we will have to have M assumption about sparsity. So we assume that each uj belongs to some sparsity class, And then we will have also to assume some sparsity condition between classes. So when beta is between 1/2 and 1, we will assume that there is no overlap between our signal, our coordinate, which are the signal. And when beta is smaller than 1, that is to say, in fact, when at least one of the two betas are smaller than 1, then we will assume that we can have some sort of overlapping between our coordinates, but in fact it's not a lot. It's smaller than d power minus maximum of beta j beta n. So our criterion, as usual for classification here, is we are going to take the maximum risk. That is to say, we are going to compute the maximum for all L and J among all the population of the probability that the classifier makes an error. And we will consider the minimax approach. That is to say, we have two types of results. One is about successful classification, and we are interested in the value of Stisa bar just in order that the supremum of the error goes to 0. And then we are also interested in the fact that there is no successful classification, which means that the errors will not go to 0, but will be strictly positive. And we will have also to display in order to get this the first result what we call asymptotically optimal classifier. That is to say, a classifier such that this error goes to 0, without in fact the n-figure, because it will be a fixed classifier. So some references. So there was a work by Peter Walt, and Gosh in 2008, and it was almost the same problem with classifier based on distance. So it was distance classifiers. There is also a work by Dono and Jean in 2009, and it's not exactly this case because they have only two classes. And in fact, it is related to the problem we consider with Urienstern and Sasha Tsibakov in 2009 also, because we have two classes, one is no signal and one is with signal. But in fact, this case can be exactly matched to this one, because it's only with some symmetry. What we are doing here with Urienstern, and we did previously with Sasha, is we are going to find the optimal classification boundary. This is what I am really interested in. We will consider, in fact, two scenarios. One with a fixed number of observations in each sample, and one when the number of observations in each sample can go to infinity, which means roughly that log of nj will be of order gamma j log d. Gamma j can be equal to 0, in fact. That is to say, nj can go to 0, but not as fast as d with some power. We can have also a variance unknown, and we can estimate it, in fact, with the samples. So first, we have two conditions that we have to consider just in order to draw the first picture. The first one is that the limit of d power 1 minus beta j a square j, that is to say the square of the signal, has to go to infinity. Because if this does not go to infinity, even if you know the position of the signal, in fact, no successful classification is possible. Especially when you have this condition. The second condition is related to the fact that if you can detect the coordinates which have signals, then you are not in fact in a problem with density d, but with a smaller density, which is directly related with the sparsity. So we have we will assume more or less, as you will see later, that square root of nj, aj is smaller than 2 square root of log of 2 log. So first, the moderately sparse case. The classification boundary, in fact, will look like this. We'll have two quantities. So this one, which is d power 1/2 minus beta j aj, And when this quantity will be for the 1, we will have some problems. And there is also another quantity which is this one, so R0J. And in fact, when this one will be also for the 1, there will be some problem. And when I say classification boundary, I mean the following. We will have successful classification will be impossible if we have one of these two cases. So as I said, this quantity can be small, in fact, or we have nj, a squared j of order 1. And the other condition is the following. You have the difference between R1j and R1L plus the sum of R0j and R0L. And when all this sum is of order 1, then no successful classification will be possible. And then you have this small condition. It's not very good. And then successful classification will be possible when the minimum of j, in fact, you can say here all the indices from 1 to m, of R1j will go to infinity. So this is related to this condition. And also, we need this condition. This is to say we have the minimum of j and l of the difference between R1j and R1l plus the minimum of R0j and R0l, which has to go to infinity. So if you have a very sharp eye, you can see that, in fact, these two relations are not completely the opposite. Okay? So first, we will have to define what we call the linear classifier. But in fact, it's not completely linear, at least at first sight. It is linear, but not after. And in fact, it's done in 3 steps. So the first part is linear, as you can see, and it is related to some sum of the coordinates, and we will compare the sum of the coordinates. So we have the coordinates of z and the coordinate of lj, that's to say of xj. So we have, in fact, 2 cases. If the sum of L are really small and for all the other, that is to say Lj, the sum are large, then we will say that psilin is equal to 0. And if L is large, or if in some cases Lj is smaller than D1, it's to say, in fact, here you have some problem with the null hypothesis. I will say that there is no signal, then you can have some problem. So we will have to define this random set. That is to say, we will have to compare the sum over z and then the sum over x. If it's small, then one more time you can have several cases. The first one, this set can be empty. So it's a real problem, and then we will take no decision. And we will go to another classifier later. If there is only one point, we have done. That is to say, psilin will be equal to j. And if we have several points in this set, then we will have to proceed to another step. So for the second step, as you can see, is more or less related to the fact that we have a large signal. That is to say, square root of nj, aj is greater than some constant, let's say, multiplied by square root of log d, in fact 2 log d. So this is one more time the classifier here. You have one more time a random set, because as you can see, you have this quantity. So you try to detect if you have one population where the coordinate can be estimated, the support of the coordinate can be estimated. So if this set is non-empty, then we can take psilin equal to j for any point in this set. And if this set is empty, then we will have to go to another step, which will be the final step for this psilinear estimator. So for the first step, what we will have to compare? We have to compare, in fact, 2 quantities. So this one, which in which appears the product of the coordinate z of z and the coordinate of the sum of the x in population J. And then we will have to take into account the square root of nj, that is to say of the number of observations in the sample. And then we compare this ratio. As you can see here, there is also in the denominator there is some sum also, depending on the difference between the size of the population. So if nj is smaller than nl, we have to compare the ratio lambda 1, and if nj is greater than nl, then we have to compare the ratio lambda 2. So we say epsilon if this is true, and if it's not true, then we will take no decision. And when we take no decision, it means that we will have to go to proceed to another classifier, and that is to say we are certainly in the highly sparse case. So the theorem is the following. In fact, the classifier epsilon does the job. That is to say, if the true hypothesis is aj, and with j is in some set, that is to say, in fact, that beta is between 0 and 1/2, then epsilon will be equal to j, and this probability will go to 0, 1. And if HL holds, and we know that L is not in this set, then epsilon can give an answer, and the right answer, because it can be L, or it will be no decision. Okay. So this is the usual lower bound theorem, which is similar to what I presented in one of the first slides. So as you can see, we have two possible conditions. And under one of these conditions, no successive classification is possible. So this one especially means that, in fact, you have population, but the level of the signal are more or less the same. Even if you don't overlap the coordinates, there is a problem because you use a linear classifier. So the proofs are, as usual, for the lower one, you use this Bayesian machinery. As usual, you try to compute, for example, the expectation of a likelihood ratio with power 2, and it has to go to 1. So this is for the case when your hypothesis is near the null hypothesis, and when you want to compare two large signals, let's say, you have to compute this likelihood ratio, for example. So you have to take into account two samples where there is a signal, and this has to go to 1. And for the upper one, you have to make some comparison of random and deterministic sets of indices and some Chebyshев inequalities, so it's not difficult. You just have to be careful for all the calculation. And then we can proceed to the highly sparse case, which is similar to what we had with Sachat-Sibakov and Urinsler previously, with only one class with signal and one with no signal. So we have exactly the same transition function, that is to say phi beta, which can be phi 1 beta, which is square root of 2 beta minus 1, or phi 2 beta, which is this quantity. And we will have, in fact, two regions, one with beta between 1/2 and 3/4, and one with beta between 3/4 and 1. One remark is that we have always phi 1 beta smaller than phi 2 beta. And we will say these quantities will be useful when we say that successful or not or unsuccessful classification are possible. So the classification boundary will be of the following form. You have to take x1j and compare it to phi beta j. This is to say, if this quantity is smaller than phi beta j, successful classification is impossible. And if this quantity is larger than phi beta j, then successful classification will be possible. And this is what we will prove. So it seems rather easy, but in fact you have to deal with several regions. What we will assume here, I will assume that the sample size nj is fixed, although we can also work with the sample size going to infinity. Beta j is between 1/2 and 1. And okay, if we have this condition, then successful classification is impossible. And for the classifiers, we have to use several classifiers depending on the region. So the first classifier, in fact, is the usual one when you have a large signal. That is to say, you can detect, in fact, where your signal is, on which coordinates. So it's the usual, you have to detect which population corresponds to this type of setting, and then you can compute your classifiers. So you have to compute this delta, which is the maximum of this random set, and then you have to compare it with some level, which let this level go to infinity. And the point where you have the maximum of delta will be equal to j. So this is your classifier. And if delta is smaller than the threshold, then your classifier will take no decision, and then you have to use another classifier. Okay, so with this classifier, we get rid of large signal in the highly sparse case. So in fact, this works. This is what this theorem says. So this classifier is really efficient for large signal in the highly sparse case. This is what is important. And then we have to use two other classifiers. One which will be useful for beta between 3/4 and 1, and another one which should be useful for beta between 1/2 and 3/4. So the first one is Cmax. As you can say, one more time, is a classifier which relies on some ratio. If you are above some threshold, then you can have two cases. It means that, as usual, we are looking at the maximum. So if the maximum is taken at only one point, it's very easy. You can choose this point. If you have several points, you can take any point in this set. And if this ratio is smaller than the threshold, then we will have to use another classifier, unfortunately. So this theorem says essentially that this classifier Cmax is good, but as you can see, this classifier is good when this quantity is larger than phi 2 beta j. And maybe that you can remember that, let's see here, okay, then phi 2 beta is smaller than phi 1 beta. So we are in fact in comparing to this bound, but in fact we would like to compare to this bound, which is okay for large. Okay. And then we have another classifier for the other region, which is much more involved because we have to compare the sum of our x with some threshold, and then center it with the function of the Gaussian probability, the distribution function, the cumulative distribution function. One more time, the classifier relies on some ratio, so you have to be very clever when you do all the calculation, and you take the maximum of all this ratio. And then, in fact, this classifier will do the following. If the ratio is smaller than some, as you can say, sequence going to infinity, then our classifier will decide that z comes from 0. And if lambda is larger than CD, then one more time we have two cases. One when there is only one maximum, so CL will be equal to J, and one with several maximum, and then CL can be any point in this set. And here, in fact, this classifier is good in the region where beta is between 1/2 and 3/4. So we have to compare x1j with the phase transition function. And we need also that xj has to be smaller than square root of 2. Okay. And in this case, here we select hj with a probability tending to 1 when hj is a true hypothesis. And in fact, for the proof, the lower bound we had for beta between 0 and 1/2 is still valid for beta between 1/2 and 3/4. So it leads to the condition that x1 or x1j has to be smaller than the square root of 2 beta minus 1. And when beta is between 3/4 and 1, then we have to do one more time this Basel machinery in order to evaluate, but in order to evaluate this quantity, we have to make some prolongation. And for the upper bound, it's as usual. In fact, you just estimate the behavior in probability, that is to say the convergence in probability of your ratio. And at last, the extension, as I said, we can also consider what we call scenario B. Scenario B is when the number of observations goes to infinity, with log of mj, which is more or less gamma j log d. One more time, in fact, you can also have a gamma j equal to 0, which means that mj goes to infinity, but very slowly. And then the noise density can be Gaussian in this case with no nominal sigma square. Thank you very much.
Thank you, Christophe. So, questions? This session.
What happens when you allow the number of classes to grow?
We don't know. We have not considered, in fact, this case, but maybe it's not really relevant when you consider application. I mean, if people want to consider real applications, it's not setting, I say, but okay, it's interesting because yes, it can be a problem because you have to define a sequence of problems with more and more populations. So maybe not very easy. Maybe you have some condition with number of observation per population also to take into account. At least to let nj goes maybe to infinity or something like this. Or maybe linked to the number of population you consider.
Okay, other questions? So, thank you.